great day, and there's more to come. Like so many of you here today, my family is an HDGC family, and we carry the CDH1 gene mutation. It's been over 7 years since we started down this crazy path, and the struggles and challenges in those early days were many. Getting our heads around this diagnosis, trying to understand the disease and our risks, receiving that first positive CDH1 test result, and another, and still more, coping with the decisions that we faced, dealing with the emotions and the family dynamics, the resurface of the grief of the loss of my mother 25 years earlier, and trying to support my brother Greg and his family, whose stage 4 gastric cancer diagnosis sent us on this quest for answers to begin with. It was an emotionally exhausting time. I spent 9 months absorbing all the information and resources that I could find, and finally felt confident in my decision to move forward with my own prophylactic gastrectomy. The date was set, September 12, 2008. Despite my confidence, there remained an unsettled feeling in what still felt like a crazy thing that I was about to do. It seems to be a recurring word, recurring theme, crazy thing. I knew in my head it was the right decision, but in my heart, I just did not want to do this. So with 3 months until my surgery date, I was on the hunt, searching for another way out of this situation. So I tracked down Professor Parry Guilford, whose work in cancer genetics and the discovery of the gene mutation I had learned about through my initial discovery process. And I remember the day I sent him that email. It was June 12, 2008, certain that there was a better way, a better solution, and if there was one to be had, he was the man that was going to lead me to it. And he wrote back the same day, no magic pill, no quick fix, no reliable options to address my stomach cancer risk. Deep down, I knew that was going to be the answer, but Parry gave me a tremendous gift that day. He gave me this understanding, his understanding, and acknowledgement of the difficulties my family was facing. He shared his positive outlook and many kind words, reminding me that things should start to trend better, in a better direction, now that we knew the cause of the high cancer incidence in our family. He gave me words of encouragement, assuring me that many people have been through this and really do well. And most important, he gave me hope for the future, for myself and my family, hope in the advancement of research that will lead to better treatment options, hope for my grandchildren, and hope for all the HDGC families I had already come to know. I had what I needed at this moment to move forward with a positive outlook, with confidence, and with hope. And like that day in 2008, I feel today is a day of empowerment and hope for all of us. We are honored and thrilled to have Parry Guilford here with us today. Parry is a principal investigator in the Cancer Genetics Laboratory at University of Otago, Dunedin, New Zealand, the Chief Scientific Officer and co-founder of Pacific Edge Biotechnology Limited. He's served on No Stomach for Cancer's Scientific Advisory Council from day one and has been a tremendous resource for us, always patiently giving of his time and expertise. I know Parry to be a compassionate, caring, and humble man, a man whose work in the field of genetics and with HDGC families has had a profound impact on the lives of so many people, many of them sitting in this room today. His presentation is certain to be interesting and educational, empowering us with the knowledge we need to make informed healthcare decisions for ourselves and with our families. I'm very excited for all of us to have the opportunity to learn about his latest advances in research, renewing our hope for the future. Parry is a brilliant man who has a wonderful spirit of fun and adventure, as I think was just exhibited with that latest photo op. He's an award-winning researcher, expert in HDGC, who, by the way, saved my family, and maybe yours too. He's a good friend, and he's my hero. And I better introduce him before I cry, so please welcome Professor Parry Guilford.
So thank you so much for those kind words. It's very, very moving for me to be here as well. I feel very emotional too. It's great seeing so many people here doing so well, and knowing that we played a small part in that is extremely gratifying. Most researchers live their lives in labs and they lose contact with the work that they're trying to do and the people they're trying to help. So we've been very, very lucky with this work to be able to meet you all and see that our research is actually helping you live happier lives. So thank you all for that, and we'll continue to work very hard on this cancer syndrome. So my talk today is a little bit on the technical side. I really want to try and convey to you an understanding of what this disease is like and how it develops. And that's partly for your information, but also, I think also it's quite empowering for you to understand the disease. I think you can often think of it as being a strange shadow lurking in your inside somewhere, but when you actually see it, what it's like, the cells, what they are like, what the molecular basis of the disease is, it feels not so scary. So I really want to spend quite a bit of time going through some slides trying to explain what the disease is. And then I'll start off with a few slides talking about the research which led to the gene being found. That was done in Tony's lab. So Tony Reed there was my boss in those years, and the lab head. And so we'll tell you a bit about that and the Maori family we worked with at that time. And then I'll go on to a little bit about the clinical guidelines, and throughout all this, I'll be trying to kind of raise some of the common questions that I hear from you about the disease, and at the end, a few slides on our current research and where that research is going, and how we really hope that the options for people this big now will be completely different to what you have now. So, really, the first wave of the research was to keep people alive, and I think we've done that reasonably well in most cases. And the second wave of the research is to really try and make the whole experience much better, try and reduce the need for the surgery. So that's the outline. We'll give it a go. So those of you who don't know, the Maori people are the indigenous people of New Zealand, and they arrived from a long time ago, down from Asia, across Melanesia to Polynesia, and they migrated from Polynesia to New Zealand about 800 years ago. There was a very famous battle in 1864. They're called the Battle of Gate Pa, and this was a battle between the British Army and a Maori tribe called Ngāi Te, and it was famous because the tribe was badly outnumbered by the British troops. They had very few weapons, but they managed to beat the British on that day. And they did that because they had an incredible set of trench. They had a mastery of trench warfare well before the onset of World War I. And they were able to beat the British on that day. So it was a very serious loss for the British, and a great victory for this tribe, Ngāi Te. But it was probably more famous not for the battle, but for the actions of some of the people from the Maori tribe. Because once the first wave of battle was over, several members of the Maori tribe risked their lives to climb back into the trenches and give water to the British soldiers who had been injured in the battle. So they showed great compassion for the enemy they had just beaten. And that woman on the left-hand side, Ni Te Kiri Karamu, she was one woman in her younger years who climbed into those trenches when there were still missiles going across and a lot of gunfire to give water to the British soldiers who were injured. And the commander of the British troops said, Ngāi Te are an enemy, anything but despicable, either intelligence or courage. So that was in about 1864. In 1964, 100 years later, a paper was published in the not so well known international journal, the New Zealand Journal of Medicine. And in that paper, a young doctor called Ted Jones described a family tree in which there was a lot of stomach cancer. And you will see, perhaps up here, at the top of the slide, in the ring there, you will see it says a Pākehā male, so that means a European man marries a princess of Ngaitarangi. And then that leads down to several generations of family, but one of these branches here is the stomach cancer family, and that branch was the one that continued on to the family we work with today. So the Ngaitarangi tribe has been involved not only in great battles against the British, but also in great battles against this illness as well. So this is the paper that Ted Jones, the guy you can see in there on the side, that guy there, Ted published when he was a young man. And in it he said, inoperable carcinoma of the stomach in a 21-year-old is a tragic discovery. When routine inquiries reveal a high incidence of malignant disease in close relatives of a similar age, further investigation is called for. This paper reports a Maori family in which gastric cancer is too common to be coincidental. So it's a story you all know. This family in 1964, there was nothing he could really do. We had no tools to try and find genes, nothing at all really. And he could do nothing but just watch the cancer come in this family. And so, as the rest of the world got on with, landed on the moon, and Nixon did his best over here, and we had Carl Lewis, winning gold at the Olympics. This family was losing a person to stomach cancer about every second year. Someone would die of the disease, and so it went on for 30 years at least. I received a letter from a GP who's now living in Canada when he described working on this family about the same time. He said that I had a young woman come into my clinic and with what he called the then fashionable disease of anorexia nervosa, and this is in the 60s. And he said, I knew very little about anorexia, but I knew a very sick woman when I saw one. And so I followed up with a few tests and was horrified to find that this young woman who's in her early 20s had very advanced stomach cancer. And he said, with great trepidation, I went and saw the young woman's mother to tell her the bad news, and she just shrugged her shoulders and saying, well, that's what I expected, because she's already lost 3 sisters to the same disease. And as he said, I've never again forgotten to ask for a family history. So this is the tribal home of this family in the tribe called Ngaitarangi, and this is their main meeting house here. On the hill behind the meeting house, up around here, it's all green now. You can just see it up here, it's all green now, but there was a quarry, a stone quarry. So in the 60s, the land was quarried by the city council because they wanted the rock to help build a new railway line to a new port being developed in their town. When the stone was quarried, a lot of bones of their ancestors were turned up. The land was in fact sacred in Tapu, and so bones were disturbed when this rock was taken by the city council. And the family believed for many years that that's the reason why they had stomach cancer in their family, was because they had been cursed because the land had been disturbed and the sacred land had been disturbed and the bones of their ancestors had been moved. So we're pleased to say that wasn't the cause, but I do recall standing outside here one day. It was the 10th anniversary of finding the mutation in their family, and we're all gathered outside, and one of the elders pointed up to the hill behind him and he said, I think the reason things are going well now is because the hill was beginning to heal. So there's still some belief in that story. So this is their circles and squares, their family tree. It's very poorly drawn. That was because I did it manually without a fancy computer program, and also I had to kind of try and squeeze it all in onto one page. But you can see the huge instance in cases like particularly down this lower branch on the bottom right, or your bottom left, sorry. There's 11 children, of whom about 8 or 9 had died of the disease. You can also see the occasional area where it's missed. So that person there, and I'll show you on the side as well, this person here, you see she's had 2 husbands and 2 families from those husbands, and each of those families have had children, and in one case grandchildren as well, who have developed the disease, but she remains well. So she is a carrier of the CDH1 mutation, but she, for whatever reason, has not had the disease develop in her. So it's not unusual for that to happen. 3 out of 10 people who carry the mutation will not develop the disease in their lifetime. This is the age of death. I'm going to get used to a few of my graphs. Sorry, there are a few of these coming up. This is the age of death from gastric cancer, or stomach, same thing, gastric stomach cancer, in this family. So on the right-hand side, out here in the green is the, and along the bottom here is the age, and up here is the number of cases in this family. We call it family A. You see that in the green there, if you're going to get stomach cancer in the wider population, you're probably going to be in your 70s or your 80s. It's a disease of normally a later age of onset. But in this family, you can see that in the red there that we had 8 cases in their 30s, there was 6 in their 20s, and a few in their teens. The youngest being a boy of 14 years of age. So that's a real hallmark of inherited cancer, is that very early age of onset, and it's no more obvious than in HDGC. So here's really the founders of this project. This is the group of people who decided that enough was enough. In about 1994, they were still having 1 or 2 cases of cancer every year, and they were always dying of the disease. They're the ones who said, enough is enough. This is not caused by a quarry on the hill and the tapu from that. This is caused by a genetic problem. And so they got in touch initially with Tony, and we began the research with them from there on. So if you want to thank somebody, thank these people here. What they were able to do is provide us with blood samples, archive tissues, Guthrie cards. I'm not sure if you have those here, where when newborn babies are born, they get a needle in their heel and a little bit of blood is drawn. And so we're able to access some of those as well. To get DNA from the people who had died at a young age, we're able to use Guthrie cards. So the family provided us with the tissue, but very importantly, they provided us with that huge big family tree of cases. Now, to find genes for cancer, now it's not so hard now, but in those days, the only way you would find a gene for cancer is by looking in a very, very big family. You couldn't find it by looking in small families. And so that big family who knew all their cousins very, very well and were able to draw that big, wonderful family tree, that was a key resource for finding the gene. And combining that with providing us with all the blood and the DNA samples we needed to find the gene. So we did a technique called genetic linkage, where you just basically search for a bit of DNA which is shared by all the people with cancer and absent in most of the people who don't have cancer. And we're able to find, after doing some DNA sequencing, that the gene was the CDH1 gene, or the gene which encodes the protein E-cadherin. Are you still with me? Is my accent too terrible? That's right. So just a summary of what's happened to this family since. Well, it's actually 2013, slightly out of date data. They've had 300 gene tests in this family since 1998. And of that 300 tests, 67 people have been found to carry the CDH1 mutation. Of those 67, 5 have chosen prophylactic gastrectomy, but the vast majority have gone the other way and gone for surveillance. Now, this is not something that we've ever recommended to them. We've always recommended that they go for gastrectomy, but it has been their choice that they don't want to have the surgery, although it's starting to change now as they see people who have had the surgery, such as many of you here, who look so well and having such normal lives, are starting to think, well, there's nothing wrong with the surgery. But for certainly the first few years, they weren't at all keen on the surgery. So we look at the outcomes from the surveillance. So there's 24 cases of cancer that have been found by the surveillance. Of that, 1 person died as a result of the surgery. And unfortunately, that was one of the leaders of the family, a guy called Rangi McLeod. We've had 2 people in whom the cancer was missed by the endoscopy and they died of advanced cancer. One person has just disappeared. We haven't seen her for a while, and she hasn't come back into the clinic for a while, so we don't know. We know she's alive, but we don't know how her disease is progressing. But we've had 20 people have had early stage cancer found by endoscopy, and they've all had surgery and they've all done very well, and they are cured of the disease. So it's out of 24 cases, or say out of 22 cases with confirmed disease, 20 people have had surgery and had their lives saved by it all. So about 9 out of 10. That's just a graph showing you the reduction in deaths in the family following identification of the mutation. Right, so now we'll get into the more difficult part where I'll try and teach you about what the gene does and how the cancer develops. So bear with me because it is a bit technical, but and also feel free to ask questions if you find it just a bit too baffling. I'll start off by giving you a tour from the stomach down into the cells, into the nucleus of the cells, to the chromosomes, to the DNA, and so you can understand where the DNA sits in this whole spectrum. So as you will all know, the stomach is made up, like every tissue in the body, by billions and billions and billions and billions of cells. And in the case of the stomach, the cells form these structures called glands. And these glands, show them over here, these big things down here, they are just holes in the surface of the stomach, and they go down and they open up into glandular areas, and those glands will produce acids which will help break down your food. They produce enzymes to help break down your food, and they produce mucus to protect the surface of the stomach from all those acids and enzymes. So that's the job of those glands in the stomach. And here's a photograph of those cells and the tops of those glands. So this is a shot of the stomach surface, and here are examples of the tops of those glands. So they don't normally have cobwebs in them. That's just a problem with the way the photograph was taken. But you can see these holes in the surface of the stomach, and there's billions of these holes in the stomach surface. And below that, you have this gland, and that gland is producing enzymes, producing acid, which is then migrating up to the surface of the stomach and being there to help digest your food. And here's the cells inside one of the glands. So if you look here's a big gland down here on the side. See this big gland here. So opening up the surface up the top here. Each of these cells here is involved in producing either the acid or the enzymes or the mucus, which will go up to the cell surface. But what you see at the bottom of each of these cells, you see a dark purple blob at the bottom of each cell, and that is the nucleus of the cell. And in the nucleus of the cell, you contain your chromosomes, you contain your DNA. So here are some chromosomes. So every single cell contains a copy of every single chromosome in the genome. And here's just one chromosome. So we're just kind of digging down a wee bit deeper as we go. Here's one chromosome just with slightly higher magnification. You can now start to see, looks like material kind of coiled, like tightly wound springs in this chromosome structure. You can see kind of breaking out a little bit there from the tight chromosome structure. So you can clearly see material wound tightly in the chromosome. That is your DNA. The DNA is wrapped around a protein scaffold very, very tightly to form your chromosomes. Now here's a chromosome where the researchers have made the kind of DNA melt away from the protein scaffold, and you can now start to see the individual DNA strands. I'll show on the left for a start. So here's, you can see the remains of that chromosome look, that kind of classic kind of X shape you saw before. It's just a protein scaffold on which all this DNA here had been very, very tightly wound around the protein scaffold. And up here, the box up on the left there is an enlargement, was enlarged over here. So you can now quite clearly see the enlargement of that over here. You can now see the DNA strand curling around. So you can see how much DNA there is in a single chromosome in a single cell. And I think it's something like a metre of DNA wrapped tightly into every single cell in the body. Extraordinary amount of information, very, very tightly wound. So that's your DNA, and the DNA is the chemical which makes your genes. And here it is again. So here's just a schematic of the DNA calling around, and the DNA contains 4 chemicals or 4 letters of DNA code, and they're called A, C, G, and T. So just 4 different chemicals which are arranged in a huge long chain through the DNA code, and the exact sequence of those 4 letters, those A's, C's, G's, and T's, is your DNA sequence. It's your genome. And there's 3.3 billion letters of DNA sequence in the human genome, and they encode 20,000 different genes. So we can look at it. Should we read some of it? A, T, G, G, T, A, G, C, T, G, G, A, T, G. And it goes on and on and on for 3.3 billion letters of DNA code. And so in most cases, in HDGC families, we'll see more of this later on, there's been a single change in that DNA sequence where one single base, one of these, we call them bases, one single one has changed to something else. It's not the right one anymore, and that has caused the gene to no longer work. And I'll explain that a little bit more in the coming slides. So we have 20,000 genes, so the genes are made of DNA, 20,000 genes in the genome, and what they do is they get copied into something called RNA, which then goes and acts as a template for proteins. And the proteins are the things which do the jobs in the cell. So the DNA is like the blueprint, and then it encodes a protein, and the protein is what does the function in a cell. If that's all been a bit confusing, just think of it like this. The genome, the human genome, is like an entire play. Each gene is an individual line in that play. The DNA is simply the paper and the ink in which it's all written, and the proteins are the actors. So you can forget all those other slides if you want to, and just focus on this one. So a gene is an individual line in a play, and a protein is an actor. Each. Right, so E-cadherin. So the gene is called CDH1, and the protein it encodes is called E-cadherin. And here's that sequence again, and this is the entire sequence of the CDH1 gene. And so I read that before, so it starts at ATG and carries on way down here to, I can't remember what far in there. So there's around about 2,000 letters of A, C's, G's, and T's in the CDH1 gene. And the E-cadherin protein, so the product of that gene, is expressed or active at the edges of cells. So its job is to try and hold cells tightly together, and also give cells information about which way is up and which way is down. It's called polarity, trying to indicate to a cell which way it should sit inside those glands. So in this picture, the big blue bit in the middle is the nucleus containing the DNA, and the red is a stain for the E-cadherin protein in somebody who has normal activity of E-cadherin. So on this side, the red, you can see the red is the E-cadherin protein all around the edge of the cell, and the blue is the nucleus there. So you can see it's really important protein in the cell. It's active at the edge of the cell, and its job is to hold neighbouring cells together. So you can see that in this slide here. Here's one big cell here and another big cell here. So a cell and a cell. And the E-cadherin is a protein there in blue, and it stretches across from one cell across to another cell and binds together to hold those two cells together. And on the inside of the cell, they're joined up to lots of other structural features inside the inside of the cell. So effectively, it's like it's a structural protein. Its job is to kind of hold the framework of one cell to the framework of another cell by binding together across that bridge between the two cells. So it kind of holds together. This is the kind of the structural parts of a cell. Those parts are all held together by these E-cadherin proteins. So mutations, what happens with a mutation? So here's the CDH1 gene again. In the first family I showed you before, the Maori family, one of these, a G here somewhere, was changed from a G to a T. So one single base change, a G to a T, in that big gene, destroyed the function of that gene, so it no longer worked, and so, of course, you all understand the consequences of that from there on. And so you all have one of these arrows here somewhere. You'll have a mutation where the sequence of the gene has changed somewhere in its entirety, and that sequence change has stopped that gene from working properly. And when it doesn't work properly, that's when the risk of cancer will develop. So back to my play. Again, this is for those who don't like the gene side at all. Wherefore art thou Romeo? You get a mutation. Wherefore art thou rodeo? Wherefore art thou Romeo? Art thou Romeo? It gets very, very confusing, right? So you can see how a change in a letter, in a sequence of letters, can disrupt the meaning and break the meaning of it all. So it's just the same with DNA. If you change that sequence of A's, C's, G's and T's and put something incorrect in there, it just doesn't make sense anymore. Okay, so it's the same logic as a grammatical error. This is the same kind of information, but shown a little bit differently. Along here is the structure of the entire E-cadherin gene and its protein. And down here, up here, I've shown the location of all those various mutations, or many of them, which ones have been described so far. So far there's been about 155 mutations found in this gene amongst HDGC families, and there's around about 350 to 400 families worldwide who have mutations in this gene. And you see there are different types of mutations. I won't go into too much detail, but two main types to think about. Some are called truncating mutations, and other ones are called splice site, missense mutations. I'll describe those in a bit because it's quite important. So again, here's the two cells being held together by the E-cadherin protein. When you have a mutation in E-cadherin and you lose that protein, and so those cells no longer hold together nice and tightly. They tend to kind of separate and they go round, and rather than losing their nice kind of rectangular shape, they go quite round looking, and so they've lost that kind of connection. And so the mutations, such as we call them, you might have seen them on your gene reports, frame shift, premature stop codon, nonsense deletion mutations, they do this. They just mean the protein is gone, and so the cells will kind of separate and round up like that. Some people will have a missense mutation, and these are very, very difficult for us to handle because it's not obvious from the DNA sequence that a missense mutation, where there's just been a kind of subtle change in the sequence, is enough to cause disease. So missense mutations don't destroy the protein, but they destroy its function. So here, in this kind of example, the protein is still present, but it's got a malfunction, so it no longer kind of recognises another copy of E-cadherin, so it doesn't kind of do its job. So the effect is the same. The cells separate and they round up, but the protein is still there, but just not working properly. So these missense problems, as I said, it causes a lot of problem because we see them quite often in families, and at first glance it's very, very hard for us to know if they are causing a loss of this function or not, and we need to do a lot of work, and a lot of great work done by a Portuguese group in particular is helping us understand whether particular missense mutations are indeed causing the disease. So if you can see that a close look at this slide. I'll start on pointing out on this side here. This is a normal stomach, and you see a red dye to show the cells on the surface of the stomach. You see the glands kind of coming down through here, but the red dye is the surface cells in the stomach. And over on here, this is the same part of the stomach, but from someone who has got an early stage stomach cancer because of a CDH1 mutation. You see those cells are no longer kind of nice and neat and rectangular and joined to each other. They're now rounded up, and they're starting to kind of look a little bit disorganized and disarrayed. They're not forming a nice, neat structure anymore. So these are called, these early stomach cancers are called signet ring cell carcinomas. And you can see why they get called that here. This is them here. See these ones all here, these big round blobby looking ones, and you see the nucleus is pushed over to one side. I'll show on this side here. These cells here, the cancer cells, the big pink blobs, and the nucleus, which normally sits near the middle of the cell or kind of clearly in the base but quite big, is pushed over. So the cells are a bit unusual. They produce lots of mucin, and it just pushes the nucleus to one side. So when you look under a microscope, you see like a signet ring. You see a jewel somewhere, and then the rest of the cell has fewer features in it. So these are the very, very early cancers which form in the stomachs of E. cadherin mutation carriers, called signet ring cell carcinomas. Now, you've probably all been kind of wondering if an E. cadherin mutation is so important for keeping cells together, or the E. cadherin protein important for holding cells together, then why haven't I melted? Why am I still here and not just dissolved across the carpet? That's because we have two copies of every gene, of course. You get one from your mum and you get one from your dad. And in the cases of HDGC, you've inherited one copy which is mutated and not working. For your other copy, the one you got from your other parent, is just fine. And that one copy is sufficient for you to be normal. You get normal development in utero, so normal pregnancy. You're just absolutely fine, nothing wrong at all, until the second copy of E. cadherin or CDH1 gets knocked out. It's called somatic. It gets knocked out in the stomach itself, and that's when the cancer will start. Hopefully I'll show this here. So here again is one of those stomach glands I showed you before. Okay, and so this could be in fact it is, this is actually a photograph of a gland from a mutation carrier, so it's perfectly normal, right? Nothing wrong with it, absolutely normal. This person has a CDH1 germline mutation, inherited mutation, everything's absolutely fine. But if a second mutation in that gene occurs, so the other copy, the copy you inherited from your other parent, gets knocked out by a mutation occurring often just by, or normally just by chance, then suddenly you have no E. cadherin at all and the cancer will develop. So for example, if you had a mutation occurring just here, which knocked out the second copy of CDH1, your cancer would develop at this point. Okay, and the rest of the stomach would still be fine. So the key event to start the cancer off is the loss of that second copy of the E. cadherin gene. And so we spend a lot of time thinking about what triggers might there be to cause that second copy to be knocked out. And really we don't have any answers to that. We don't think there are any major obvious triggers. It's most likely, in most cases, it's a chance event. Mutations occur by chance all the time, and to understand that, just think about trying to copy those 3.3 billion letters of DNA code every time a cell divides. And these cells, they divide every 3 to 5 days. So every 3 to 5 days, they've got to copy 3.3 billion letters of DNA code and get it right. And so every 3 days, it's copied, and if a mutation occurs, it happens to occur by chance in the CDH1 gene, and suddenly someone who already has an inherited mutation has no E. cadherin at all, and the cells will they'll let go of each other, they'll round up, and the cancer will start from there. Relation. They often have mutations in CDH1 as well, so their disease is identical to the disease in the HDGC families. But where it differs is that both their mutations have occurred just in a particular cell. So here's a cell here. They've had two mutations in CDH1 occurring in that same cell, and then they'll develop diffuse gastric cancer just like people from HDGC families do. And that explains why the cancer occurs at such a young age in the HDGC families, because one of the mutations you need to develop the disease is present from birth, present from conception. It's there straight away. Separate hits on that gene before the disease will develop. So that's why HDGC families, the cancer often occurs in people in their 20s, 30s, 40s, whereas in the wider population it's much more likely to be in the 70s and 80s, because they've got to get an extra mutation occurring before the disease will develop. Is that clear? Right, and so how does CDH1 mutation lead to cancer? We'll give you our best guess of this. So we've seen this before. You've seen the glands in the stomach. So here's our model of how the disease develops. Again, I must stress it's a model. You might have heard the expression, all models are useful, but all models are wrong. This is probably like that. It's pretty good, but we're sure there'll still be some errors in there somewhere. But it's I think fairly close. So here's again one of those glands. Remember, you've got billions of these glands in the stomach. When you get the second copy of the gene is knocked out in a particular cell in the stomach, just probably by bad luck, occurring. Its second copy knocked out in this cell here, so this little cell here has lost a second copy. It lets go of its neighbours, it starts to round up, it starts to lose a sense of which way is up and which way is down, and it will move out of the gland structure to sit just outside it. And when it sits outside the normal structure, it's away from, it's like a classic kind of society, it's away from all its fellow cells, and it starts to behave a bit like a rogue. It's no longer part of normal society, working in a team to try and produce enzymes and acids and mucins. It's now sitting out from the main mass of cells, and it just starts to do its own thing. It's as simple as that. So it's really a very simple event. A cell loses its normal contact with other cells, it squeezes its way out and sits in a new environment where it's no longer getting the normal signals. It's no longer got its brother saying, John, this behave yourself, it's just out of hand. It's sitting there and it's not hearing the normal signals from the neighbouring cells and just starts to do its own thing. And it will grow to a certain size, often to say a millimetre or two, and then we think it will sit very, very quietly for quite a long time. In fact, we think many of these really early ones will actually kind of fade away and die as well, and they'll be replaced by others. And so when they are doing the biopsies during your endoscopy, they're trying to find these little guys here, these little small foci of cancer, which they can't see very easily, but they're trying to just pinch them out, and then they'll have a look with the microscope later on and try and find signs of them. But we're very, very confident that these little foci of cancer are really quite indolent. They don't develop cancer very rapidly. They will sit there really quietly for quite a long time until something else happens. So probably another mutation in another gene is required for the disease to develop, maybe more than one mutation. So you can have these little foci of cancer sitting there very, very quietly, nothing much going on, until by chance another mutation occurs, and then that mutation makes that cancer cell much more aggressive and will start to divide rapidly and start to move rapidly, and then the cancer will become clinically relevant. But before that, it's a very quiet and indolent disease. So this is going to try and explain why only 7 out of 10 people who carry the mutation go on to get the disease. We think it's due to these chance events. To get a full-blown cancer in HDGC, you need to have obviously the inherited CDH1 mutation. You then have to have the second copy has to be mutated or knocked out, and then you need mutations in other genes as well to occur before you get a full-blown cancer. And because these are chance events, these second and third steps are chance events, well, they're quite frequent, but they're still chance. There are people who have this mutation, who don't get that and don't get that, or they might get this but not that, who do not go on to develop really nasty disease. And that's why I showed you the pedigree at the start. Some people can have the mutation but live a life of a normal length. It's really most likely just to be good luck. Right, so is that clear? Do you kind of feel that you understand a little bit about how the disease develops? Right, so now into the we had a question.
Well, I didn't know if they knew what those other genes were that, no.
No, we've got a clue what some of them might be, but it's still ongoing research on what that is, yeah.
If a family member has the CDH1 gene, but doesn't develop the cancer until mid to late 60s, and it's still early stage, does that mean other family members who have the gene have a similar mutation that wouldn't develop till late?
Yeah, we don't know. I mean, probably not. It may be that it's just purely luck, but it may be that for someone who develops the disease later in life, or not at all, may have other genes in their body which give them some degree of protection from the cancer. And we've got no idea what those genes might be, and whatever they aren't terribly powerful, but we think they might be around in some families. Like we see strange things which we can't explain. The Maori families, always a really young age of onset. We see other families where it's a good 10 years later, So we suspect there are other genes around which give some degree of protection and might delay the development of disease, but as I say, we have no idea yet what those other genes might be. Right, so I want to go through some of the clinical management issues and also a few words on the new clinical guidelines which we just released, or about to be released this month. So the management options are as follows. You can have pre-implantation genetic screening, or associated with IVF. So you can look for if you choose to have in vitro fertilization, you can have the developing embryos can be tested. A single cell can be taken away from that embryo, be tested for the presence of the CDH1 mutation, and if it's present, they would not implant that embryo. They would choose another one which did not have the mutation. So that is one option that people have to remove the gene from their lineage forever. It doesn't suit a lot of people, and so of course we have to keep on looking at other options. Surgery, of course, is the one that we all know a lot about, and I won't talk much more about that. Surveillance or watchful waiting is something which, as I showed you, is still quite common in New Zealand, although we don't recommend it. And then where we're hoping to go with the research is chemoprevention, or that is to try and develop drugs, chemicals or drugs, which will prevent the disease developing. So the last one is still in its early days, but I'll show you at the end a little bit of our data to give you an indication that we're on the right track, and we're very confident that we will actually have a good chemoprevention compound to use, not for people in this room, unfortunately, but for the ones who are about this high. We think we will be able to give them something which is much better than a gastrectomy. So I just want to clarify for you all why we recommend gastrectomy rather than the surveillance. This is a bit of stomach tissue again, so you can see those nice glands on your right. Over here you can see the nice gland structures here. So this is where the food comes down, so your McDonald's burger arrives down through here somewhere. This bit under here is one of those early stage cancers. So it's full of those little signet ring cells. So on the side you can see where the cells are no longer forming a nice structure, they're no longer working as glands, they're just sitting there, dividing, they're not doing anything, they're not helping the tissue. Notice that they sit underneath an intact and fairly normal looking surface. And so when the endoscopist comes along with his scope and his bright light, he will be looking down here and he will struggle to see this underneath the surface. He won't be able to see through this layer here and see this focus of cancer. A lot of other cancers, they form polyps, and so it's very obvious. Classically the colon cancer, you can see a polyp and it sticks out from the surface. These ones don't do that. They will develop and divide under an intact layer of cells. After a while, the endoscopists get very, very good at it, and they can see the bigger lesions because for some reason, perhaps a change to the blood supply, this area across here looks a little bit pale. It's a little bit paler than the region of the sagittal. So a very skilled endoscopist can often see a focus of cancer when it's got to about 1 centimetre in size by just spotting that kind of pale look to it all. And I'll show you some slides of that in a moment. But very often these foci are very, very small and they just simply cannot see them. And so it's very, very, very easy for them to be missed. I'll try and get this to go. So this is an endoscopy. So just before we start, we're going down the person's stomach, and don't worry about all this black stuff. That's just some dye which has been washed away, methylene blue dye which has been washed away. Now I want you to look at this and tell me where the cancer is. So this is a germline mutation carrier. There somewhere. Right, that's it there. That thing there, that pale spot there is the cancer. Right. And so that's a really big one. And quite frequently they're very, very small. That's a big one. So you can understand why the endoscopists are nervous that they may not see the cancer. It could be missed. Okay, so you know, some people who are very experienced with endoscopy and HDGC will do a lot better than others at seeing these very flat, pale-looking lesions, but they will still miss them sometimes. So here's a couple of other shots, and also some indication of some new research which has been done to help find them more easily. So here's a little pale lesion. Okay, so very, very hard to see. That little kind of pale patch is a signet ring cell carcinoma. And here's a new technique people have been using with endoscopies called narrowband imaging, which helps you see those lesions. They're a bit clearer to see. It's a wee bit more striking. So it's a possible improvement we might have in the future for screening patients, people who choose surveillance rather than surgery, but it's not ideal, and it really still only picks up the bigger lesions, and we'll still struggle to see the very small lesions. But at least it's a step in the right direction. So again, I made this point earlier, I'll just make it again so it's quite clear. Our first big Maori family, in between 1998 and 2013, 67 mutation carriers, those who had surveillance, 24 cancers were found, 22 were early, 2 were late. So 22 out of 24 people had their cancer found by endoscopy, 2 had the cancer missed and they died of the disease. So that's roughly, in my view, realistic risks that you undertake. If you choose surveillance, 9 times out of 10 it will be found, but 1 time out of 10 it will be missed. So you can understand by taking that option you will reduce your risk of dying of the disease dramatically, but it will not eliminate your risk of dying of the disease. What we see is that the choice that people make, particularly in New Zealand, the Maori families, is whether they go surveillance or surgery depends on their appetite for risk. Some people are pretty relaxed. Look, the doc will, if there's something the doc will find it in my scope next year, it'll be right. I'm not worried, and carry on normal life. Others are thinking, every time my stomach hurts, that's the disease, and it's away. I'll be dead by Christmas. And so, two groups of people. They go two ways. If you have an appetite for risk, then you may be quite happy to jump off the iceberg first for a swim. But we don't recommend that because there are risks lurking in that deep cold water. So again, I'll just say again, I would really rather you had your surgery. But it's no great panic. If you're having good quality surveillance, your risks are still really pretty low in any given year of getting advanced disease. So choose a time which is right for you, but please go ahead and have that surgery when you get the chance. I want to go now through a few of the clinical dilemmas or questions, some of the questions which you have already sent in to us. I mentioned before the thing called variants of unknown significance, which this is when you have a mutation in the EKT gene, which we just don't know quite what it means. We give it a fancy name, variants of unknown significance. It just means we just don't quite understand it. That's a real problem for us all. Most of the mutations, I'm sure all the mutations of people in this room are quite clear that they destroy the gene's function. Other ones, it's not quite so clear. We have to do a lot more work trying to understand what the mutation has done. That's called the missense mutation. So that's an ongoing problem. No easy fix to that. But as we get more and more experience and more families are described, and we start to see what mutations they have, we'll learn more and more about which ones are the nasty ones. Pregnancy. Now this was, I can't add any more to Rachel's wonderful presentation earlier on. It was tremendous. It's, we've had in New Zealand too. Plenty of people now who've had their stomachs removed have gone on to have great pregnancies and wonderful healthy kids. So we don't see any major or any concern there at all. As long as I think you really want to start your pregnancy in a good shape yourself. You don't want to be still struggling with the issues post gastrectomy. So once you're stable and settled and you think you're holding your weight, then absolutely no reason to not to start a family. One thing which is coming up increasingly is CDH1 mutations in the absence of a family history of stomach cancer. Now we're seeing this a bit now because it's getting easier and easier to test for mutations, and so now what is happening with people who are getting tested for a high breast cancer risk, breast cancer in their families, but no stomach cancer in their families. I've been tested for the normal BRCA1, BRCA2 genes, but now they're thrown in CDH1 as well, just because they can. And that's meant we've seen remarkably a few families have turned up, and it'll just increase in number, who have no stomach cancer in their family anywhere, but they have a nasty CDH1 mutation. Now, we don't quite understand what this is all about just yet. It might be, as we discussed earlier on, there might be another gene somewhere in those families which is protecting them or delaying the onset of stomach cancer in that family. Or there's a lot of chance in this world, and it could just be another chance thing. There might be a really small family. They may not have yet had a chance to develop disease. They may not know all their cousins. There might just be small subships, so they just haven't really had a chance for the disease to develop. So we just don't quite understand it yet. It is a dilemma for us. And what at the moment we recommend is that people who don't have a clear history of stomach cancer don't just go straight out and have a gastrectomy, that they take a surveillance option until we can be more confident of what's going to happen to them. So we don't really want people just going and having a gastrectomy based purely on the evidence of CDH1 mutation. We really want to see the mutation plus some history of stomach cancer. This is a stomach from a 15-year-old girl from that family A. Now, you can see the black spots. These are just coloured in there, but the black spots show the actual size and location of the cancers in this 15-year-old girl's stomach. So she had about 300 different foci of stomach cancer at 15 years of age. So one of the kind of, it's a real conundrum for the endoscopists who are doing the screening, and they're taking random biopsies, trying to catch one of these guys. And when they catch one of these guys, they'll say, look, we've found an early stage cancer, have your stomach removed. But really, I can guarantee that majority of mutation carriers will have those foci there somewhere, and they just haven't yet been caught by the endoscopist. They're sitting there, they're quiet, they're indolent, they're not doing any harm, and they may stay that way, but they are sitting there. And so, in some ways, the endoscopy is important simply to say to the person, here is proof that you have early stage cancer. But really, the cancer is probably there anyway. It's not life-threatening, but it's probably lurking there. And but the great benefit we get from the endoscopy is that proof, here is a cancer in your stomach. And so for many people, that's all the information they need to make the decision to have surgery. Some people just need that information. They cannot go ahead with surgery without that direct information. Right, so other questions. Laparoscopic surgery, it's been increasingly used by the surgeons. Unfortunately, we're at a time where this type of surgery is in a growth phase. It's been used more and more and more and more. So surgeons are really keen to use it, which means a lot of surgeons who are offering to do your operation are still learning the technique. They aren't good at it, they're just going to give it a go and try and learn the technique. And of course they have to practice, they have to learn, they've got to do it, they've got to gain experience. But we strongly believe they should not gain experience on HDGC patients because you're well, you have long lives ahead of you, you don't have disease of any clinical note. There's every reason you're going to live for another 50, 60 years. You know, you could argue that you're better off to do the surgery on someone with advanced disease who might be in 60s, 70s, who, if things go wrong, then the consequences are not as dire as losing a 20-year-old who is otherwise well. So we really recommend, if you're going to have surgery or some of your family members are going to have surgery, that you have laparoscopic surgery if the surgeon has done a lot of them, is really good at them. You don't want to be part of his or her learning curve for that technique. So there is some gains by having this approach. You will get out of hospital a little bit earlier, but really that is nothing in a lifetime. I think in most cases you're better off to have proper chop where they can get in there and have a good look. Sure, you'll be in hospital for a wee bit longer, but your chances of having the job done well are probably greater as well. So just let your surgeon know that you're not happy with being part of his learning curve.
In your experience,
Lifestyle triggers, well,
in your experience, what is a lot?
Pardon?
Like, what is
Oh, what's a lot? Yeah.
How do I define that?
Yeah, a lot. I would think a lot would be over 100. If the surgeon is experienced gastric surgeon has done 100 laparoscopic operations as well, I think chances are he knows what he's up to. But if he's done 10, I just wouldn't go anywhere near him. The lifestyle triggers. I mean, this is a really difficult area, and we thought long and hard about this for quite a few years, and we really came up with the big zero. We cannot find an obvious lifestyle trigger. We've looked at smoking, we've looked at drinking, we've looked at H. pylori, and we've looked at dietary things. Not in any kind of formal studies, but just anecdotally, and we haven't found anything obvious. We've got from our family, some of the Maori people are pretty hard. They live life pretty hard. They drink a lot and they smoke a lot and they yahoo a lot. And we've got one guy who's in his mid-70s and he's a mutation carrier, and he is absolutely fine, and he drinks like a fish, smokes like a train, and just really misbehaves all the time. And he's fine. He's fine. And so all our classic risk factors, he has them, but disease, no disease. So we are really struggling with that. I mean, but still, of course, we recommend if you have H. pylori found, get it removed. It's a good idea anyway. It's a good idea to eat a diet which is kind of healthy and varied. So just do that anyway. But we'll be surprised if there is any single major lifestyle trigger which brings it on. But I could be proven wrong, and it'd be nice if I was. But at the moment, it doesn't look to be anything that simple. Again, I think luck could be an important part of it all, or other genes which might be lurking around there as well. But lifestyle factors, triggers, I think less likely. Right, new clinical guidelines. Now these are important because Karen was involved in writing these, so you can blame her if you don't like the wording. I don't want to go through all this, but it really hasn't changed too much from what we saw before. Apart from the criteria for how we define the families, the bar's got a bit lower so that we can test more and more people than we did in the past. So now you really only need to have 2 people with diffuse gastric cancer in your family. You don't need to worry about the age limit quite the same anymore. So it's become a lower bar to get a NECAD adherent test now. But otherwise, it's really roughly the same. In your 20s, you're encouraged to have prophylactic gastrectomy. And if you choose not to, you have yearly endoscopic surveillance until such time as either the endoscopist sees one of those white lesions, or he gets lucky with his pinch and pulls out one of those early cancer cells. But there's more and more awareness and understanding of the need for good nutritional care, and I think that's starting to occur now. There's an awareness that we have to be more careful with lobular breast cancer, and then so MRI screens are recommended from age 30 on. But nothing too majorly different. But I think very soon that this document will be available to everybody. In fact, a very exciting initiative from the Stomach for Cancer is to translate this kind of technical document into something which everybody can read. So developing a lay version of this document, and that'll be done over the coming months, I guess, and hopefully it'll come out on the website or wherever.
As soon as they're done, they'll be there.
Yep. Right, so you must be sick of me now, so I'll just wrap it up with a few more slides on the hope for the future and the research which has been done mainly in our lab, but also just want to acknowledge work in other groups as well. So a lot of groups around the world have an interest in the endoscopy, trying to make that better. I showed you one example of that earlier on. So plenty of groups here in the US and in Europe and in New Zealand as well, are trying to improve that technique, and so that will get better in time. A lot of people are doing studies on patients post-gastrectomy just to follow them and look at the problems and look at ways to try and minimise the issues which occur post-gastrectomy. A lot of groups, including ours, are looking for genes other than CDH1 which might cause HDGC. So we often find, in fact about half the time we find people who have a family history of stomach cancer don't have a CDH1 mutation, so we're trying to find other genes which could cause similar disease. Nothing to report yet, but we think we're getting a bit closer. But certainly CDH1 is going to be the major gene. There's nothing terribly obvious as being a common second gene. There's groups in the US, there's a group in Portugal doing a lot of really good work on the mechanism of the progression. Someone asked a question about what the other genes are which help the disease develop and progress. They're trying to identify what those genes are. Triggers, I mentioned, we're not sure where to go with the triggers, but I know at least one group in Australia who are doing a formal study into that, trying to identify what they might be, and good luck with that. Genetic factors which increase risk, again, there's a group in Australia trying to find those. Again, it'll be a long, difficult study. And finally, drugs to prevent cancer development. So this is chemoprevention, and this is the work that we're doing in our lab in Dunedin in New Zealand, and I think there might be a US group starting to get an interest in this area, but largely at the moment it's just our lab. And what we envisage is a drug which can be used alongside surveillance. We're not saying that we can throw away surgery, throw away surveillance, but what we hope for the little ones, when they get to be the age where they should undergo surgery, we can say, how about surveillance plus a drug to reduce the risk of that disease developing. And I'll show you what we've been doing very briefly and why we're kind of encouraged, and also the kind of the logic behind it as well for your interest, but also I'd love some feedback on what you think about the approach that we have in mind. So there are two ways you can think about doing chemoprevention in the families. One is to stop this first event. So when that second copy of CDH1 is lost and the cell pops out, you could try and stop that happening. And we started looking at that and did some lab work in that, and I increasingly became despondent that we wouldn't be able to succeed with that, because you would need to take a pill a day. And I know Karen wanted a pill a day, and I was trying to make her happy, but I just increasingly felt that we wouldn't be able to get a pill a day which was safe and tolerable. It's very, very hard to find drugs which are tolerable and actually do something. There are not many aspirins around, and even that causes problems for some people. So I just started to feel that it was going to be an inefficient use of our time to chase a chemical which was going to stop these cancers developing, but you could take it every single day and not get nausea or other kind of side effects, lethargy. Which, if you've got those, of course, no one will take the pill and it'd be a waste of time. So I just decided in the end that it wasn't an approach which I really wanted to pursue. We still have an open mind to it all, but at the moment our focus has gone off that approach to the second approach, which is trying to knock out these guys, and these guys as well, but knock out the early lesions, the ones which sit there in often large numbers and don't do very much, and are likely to, but not certain to, progress into nasty cancer later on. So what we plan to do, and again I love your feedback on we think this is a good idea or not, is to knock out these early stage cancers, just kill them. And so what we would envisage is that, because we think the time to go from here to here, 4 or 5 plus years for a lesion like this one to get into something like that bigger one, so to go from here to here, probably about 4 or 5 years for that to happen. So we believe that gives us a window where we can treat individuals and knock out these early foci, kill them with a drug. And then the plan would then be to let the people go again, back out into society, and then drag them back in again 4 or 5 years later and repeat the same drug treatment. So we envisage a treatment it'll be chemotherapy, but it'll be a mild chemotherapy. It won't be very toxic. We don't think. We're working very hard to keep it low toxicity. And so the plan would be to, every 4 or 5 years, take mutation carriers who've decided not to have surgery, because again, surgery is still going to be the safest option, but this will be the next best thing. You're having surveillance, but every 4 or 5 years we whisk you away, and you have a cycle of treatment to destroy these early stage cancers. And we think we can do this indefinitely, in principle. So we think it's a step in the right direction. I know it's not the simple solution that we'd all look for, but I think this is the next logical step for us to try and manage the disease. So what we've been doing to try and achieve that goal has been doing these very big drug screens. And what we've done is we've taken some cells which have ecadherin and cells which are identical but don't have ecadherin. So a tube of cells which have ecadherin and those which don't have E-cadherin. And we throw a drug on those 2 tubes, and we look for ones which cause more death in the E-cadherin negative cells than the E-cadherin expressing cells. And those are the drugs which should be useful. They should kill those early lesions and leave the normal tissue alone. So they should have low side effects because they're not touching the normal cells, but they should be killing the E-cadherin negative cells. That's the logic. And so what we've done so far, we've done 2 screens. One was with 4,000 known drugs. This is drugs which are already in clinical use. Okay, so they've already been through the clinical trials. They've already been used. They're known to be generally safe. We looked at 4,000 of them, and we found a handful looked kind of promising. They were causing more death in E-cadherin negative cells and leaving the other cells alone. So that's our first wave of candidates we think might be useful for chemoprevention. Especially since they're known drugs, they've been tested in the clinic, they've probably been used very, very widely in the community, so we know they're not particularly toxic. So we need to kind of choose the best one of those and take it forward into further studies. We've also done a huge compound screen, so 114,000 new compounds. So we don't quite call them drugs yet because they're just chemicals, but 114,000 compounds. We did the same experiment, cells in the tubes, and throw in the drug 114,000 times. We use robots to help with that. We didn't just get the students to do it all. And that has turned up about 83 compounds which look extremely good. They cause strong killing in the E-cadherin negative cells and don't touch the E-cadherin normal cells. So we think we've got the basis of some very promising compounds. So this is a bit of technical data which I'll just bear with me. This is one of the known drugs. It's called entinostat, an HDAC inhibitor, and this is a time course study. And so along here is time to 0 hours through 50 hours on both graphs. Here are the cells with E-cadherin, cells without E-cadherin down here. And what you're looking for is, on this axis here, is cell growth. The number that the cells are doubling and growing. And so on the top panel here, at about 4 or 5 different drug concentrations, you're seeing the drugs there, but doesn't care. It carries on. The cells are dividing normally at those concentrations. But if you look in the lower panel down here, you see with the different increasing drug concentrations, the E-cadherin negative cells are going, they're not growing anymore. It's just been stopped by this drug. So we think this is the kind of thing we want to see. We want to see the E-cadherin expressing cells of the normal cells in your stomach and the rest of your body sitting there, don't notice the drug. But the ones where E-cadherin is lost, so those little signet ring cells, for example, they are getting the feel of the drug, and their growth has been stopped by the presence of that drug, and you see a greater effect with a higher concentration. This is one of our new compounds, and just to make it complex for you, I've done it a different way. This is now increasing drug concentration along the bottom axis here. So from low concentration to very high concentration of drug on the bottom axis, and on the vertical axis is cell survival. Now the blue dots are the E-cadherin expressing cells, the green triangles are the E-cadherin negative cells. So what you can see here is, look at the blue dots for a start, increasing the amount of drug, lots more drug, lots more masses of drug out here. They don't care. Those cells don't even see the drug. But the E-cadherin negative cells don't care about here, don't like this, don't feel very well, and they just start to die away really, really dramatically. So we think this is another extremely positive compound. We've got 83 which are doing a very similar thing. So what we have to do now is take these known drugs and these unknown drugs through several more steps of research before we can think about going out to clinical trial. So, for example, the shortest path is for the known drugs. There we have to do some more work in our lab models so we can grow grow those tumours in culture, and we can look in more detail at which ones are working best in those cultured cells. And that's not a long experiment. It will only take a matter of months to do that experiment. A harder thing is to develop a mouse model. So we can't just start throwing drugs into people like you without having a great confidence that it's going to work. I mean, we'd love to be able to go straight to human studies, but we have to ethically, morally, all these things, and logistically as well, we have to be confident the drug is going to work. And so we need a model system, and there we will use mice. And so it'll be a mouse experiment. We will develop a mouse which gets HDGC. We know that this can be done. We've kind of done it before already in a fairly crude way, and we're going to work now on a new improved mouse which gets a disease very similar to the human disease. So it'll take us a while. It'll take us about 2.5 to 3 years, assuming we get our funding, to develop that mouse, and then we'll start to give that mouse drugs, and we'll give them drugs for a while, and then we'll kill the mice, get the stomachs out, and look to see whether we've killed the cancer in those mice. So I know it's not always great to have to do these animal experiments, but we simply cannot take drug and go straight to humans, because we would cause people to die unnecessarily. Once we've done the animal models, then we would go into human safety trials. In the case of the known drugs, we don't need to do that. They're all out there. We know they're safe drugs, so we can go straight from those mouse models to human studies. And so that could start inside about 5 years. The new drugs, those exciting new compounds, we've got a lot more work to do. We've got to make them a bit stronger than they are now. We've got to make sure that they're just working as well as they possibly can. We then will need to do the human safety trials, so we have to make sure that they don't make people sick. So that will take a lot more time to develop those. So probably 8 years before we can get any of the new compounds into clinical trials. The way we see the clinical trials working, and this is important, is that we think we're going to have to get people from the families who have made the decision to have their stomachs removed, and they intend to stick to that decision. They want the safest option possible, which is stomach removal. What we will probably need to do is get people who have made that decision to volunteer to take our drug for just one cycle, sometime between their decision and having their surgery. So then we can get their stomachs, open them up, and see whether there's any sign of these really small cancers. You can't see them often with an endoscope, as you know. We'd have to get the stomach out, and we'd have to examine them under a microscope in great detail and see whether any cancers were there. And this might take a few attempts, but we think in time, it shouldn't take too long. We would get one of our compounds, if it's done well in all our other studies, would consistently give no foci, next patient, no foci. We see that for, maybe a dozen people. We could then say we're pretty confident now that this drug is killing the cancer in humans, and we could then go to clinical trials on people who have taken the other path, people who have already said, I want to have surveillance, I don't want to have my stomach removed. We would say, right, you take this path, but take this drug at the same time. And there, it's open-ended. We then just really have to follow those patients and follow those patients and follow those patients to see what happens. So unfortunately, it's going to take a long time, but at least once we get into those human studies, we hopefully will be giving people good compounds which will kill those cancers, and they can expect a long, healthy life. So that's it really, apart from thanking people in the lab who've done the work. I sit in my office and worry, that's about all I do, and everyone else does the work out in the lab. A lot of our money for our research has come from the New Zealand Government, the Health Research Council, so great thanks to them. But of course, we've also had some great financial support and moral support as well from No Stomach for Cancer for many years as well. So thank you very much, and happy to take questions.
You said some people have the gene positive, but they can live into their mid-60s, drink, smoke, whatever. Does that give you some indication that some people's own bodies, their own immunity, is fighting that better? And if you look at this end of it, building the immune system within one person's own body by studying how these people's bodies fight the cancer cells.
Yep. I mean, that's a very real way that some people might get protection. We're not kind of super enthusiastic that immune strength is going to be a major player here, because the reason I say that is when we look at these early lesions, these early foci, we don't see immune cells around them. They don't seem to be being recognised by the immune system. So I think they're still seen as being normal by the immune system. So you could have a super strong immune system, made even 10 times stronger than normal through great herbs and spices and whatever you might dream of. And I still think they would probably fail to recognise those very early lesions. But what they might do is recognise the ones which have started to progress and turn nasty. So I completely agree with you. I think it's a good point that immune strength may in fact be an important thing we could try. And one feature, I've been here for a big conference, and one of the most striking research themes at the moment is immunotherapy to try and destroy cancer, and it's looking very promising for many cancers. So I think it's something we'll certainly keep an eye on and see whether somehow we can further engage the immune system to help it knock out any of the bigger cancers they start to develop. So, yep, nothing we can offer immediately, but I think certainly something which is important.
At one point, I think I read that you were doing studies with valproic acid.
Yep.
What has happened?
Yep. So it didn't go so well. That was when we were thinking about the trying to prevent the cancer starting in the first place. So what we found is that it was kind of useful in the lab. We could kind of get the E-cadherin gene to be the other copy to be nice and strong, and that was fine. But the concentrations of drug required to do that were enough to make people sick, and so that was really what kind of drove us away from that approach, because it was a drug which we really liked it because it's been used by people for many, many years for other things, but the concentrations we needed to be confident it was going to stop the cancer developing were really high, and so in the end we stopped those. But interestingly enough, that class of drugs we think is very, very important, and we're still pursuing that class of drugs as ways to kill the other lesions as well.
So this E-cadherin, is it unique to the cells and tissues of the stomach? Why are we not seeing cancers in the liver, the uterus, the lungs, not
Yep.
block? Why the stomach?
Yep. We don't know on stomach and breast, so we don't know why that is. It is expressed in every epithelial tissue in the body. So that's lung, that's in skin, that's in pancreas. It's everywhere. But we don't really know why we only see stomach cancer and increased breast cancer. It's probably because there are other genes which compensate for loss of E-cadherin in other tissues. The E-cadherin is a member of a really big family of very, very similar genes, and we suspect that in other tissues, other family members compensate for the loss of the E-cadherin. So you lose E-cadherin, another cadherin just lifts its game a bit and compensates, but in the stomach you don't see that.
Yeah, my wife was diagnosed last summer with lobular breast carcinoma and fell into the group you mentioned where they ran a huge panel. CDH1 comes back positive. She has 3 siblings, all in their 40s. None of them have gastric cancer. She got it from her father, who has 2 full siblings and about 6 half siblings. Extended family, nobody has any history of gastric cancer.
Yeah.
I guess I have kind of a 2-part question. I think you've already answered the first part, but I just want to be sure in that situation, you would recommend that she undergo annual surveillance using the Cambridge protocol.
Yep, that's correct.
That's
yep.
what the new guidelines are going to say.
Yep, that's right. The new guidelines just say treat those individuals. The decision for surgery should be made with caution, I think, are the words. So I think that it read into that what you will, but to me it means you don't just go straight ahead and have a surgery. If your wife is very anxious about her stomach cancer risk, then maybe surgery is the right thing to do for her. But really, the best thing is probably just to have surveillance by the Cambridge protocol every year, because it might be that the cancer will never develop. Stomach cancer may never develop in her family for some other reason. So it would be very unfortunate to go ahead with aggressive surgery when it was never required. So we might find in a matter of years we understand it better. We can say definitively that you will never get the disease, or in fact you do have the same risk as others, but you've just been lucky so far. So for now, it's really a cautious approach. But the guidelines, the guidelines are really suggestions. It's nothing there, which is in black and white. And so if your wife is really, really uncomfortable with living with an EKT mutation, having simply surveillance, then I think it would be reasonable for her to discuss gastrectomy with a surgeon. You know, we're not saying no, it can't be done, but it's just saying treat that issue with great caution. And at the moment, there's no real evidence to suggest that gastrectomy is the right thing to do. I know it leaves you in a grey area, but we can't force.
The second question then is, how many family members should we? I mean, I guess ethically, I kind of feel like we need to tell the rest of the family that you've got at least a 50-50 shot right now, as far as everybody knows, of having the same defect. I would guess that would be a reasonable thing to do.
Yeah, absolutely. I think it's a very good thing to do, and so everyone who you think may be related should really have a test. And it's difficult for them; it'll come out of the blue for them, but it sure beats cancer coming out of the blue.
Is there any molecular imaging or PET imaging that's going to research along this to try and detect early gastric cancer? I don't know about the PET approaches. Not really. I mean, people are trying to improve endoscopic approaches. It's just really difficult with a multifocal disease where there's 10, 20, 30, 200 foci in people's stomachs, and what you're trying to, which will be there, probably going to be there from birth. Many of those foci will be there from birth, and so you're then asking to see a focus of cancer which has changed to be more aggressive. It may be a very small change, but it's now become more invasive. It's had an extra mutation or two. So to see those with classical imaging modality would be very, very difficult. So, thank you.
This isn't something your neighborhood endoscopist can do. Surveillance, it's specialized tertiary care.
Yeah, it's very much so. There are some quite clear recommendations in the guidelines on how it should be done, but the most critical thing is that it's done by someone who has seen HDGC before, because a lot of the regular endoscopists just won't see those pale lesions. They'll just look straight past them and say, no problem at all. I mean, they'll probably be more careful around ulcers. They might biopsy more carefully around ulcers, but they won't have the eye, and it is like a trained eye which will see those foci. So it's very, very important that if you are having surveillance, you have it done by an endoscopist who is familiar with HDGC, understands the disease, and has seen those lesions before.
I know your specialty is with the gastric cancer, but could you talk at all about someone who has the HDHC and had the prophylactic gastrectomy, what the surveillance should be for the lobular breast cancer, or what the guidelines are going to change?
The guidelines, I think it's yearly MRI from age 30. And you can have mammograms as well, but they don't do very well at picking up lobular breast cancer, so it's yearly MRIs. And by all accounts, that works quite well at finding early stage disease. So it's less of a problem than the stomach cancer. Yeah.
I know in our family there was a connection with colon cancer and stomach cancer was a piece, and it sounds like there's really not enough evidence to show that there's no statistics on colon cancer. Do you expect that to change, because that certainly saved our lives?
Yeah, I don't think it seems now that we've seen enough families that we know that it's unlikely that colon cancer is going to be a major part of the syndrome. So your risk might be up a little bit if you have an EKT mutation, and some of those colon cancers are probably going to be EKT related, but I don't think many will be. So I think the best thing there is really just to go with your country's best guidelines for screening for colon cancer, and and that actually means doing something. It means you go and have a colonoscopy, and when you're say 50, you have other tests which are available, other blood and stool tests which are available now. You do that. You do the recommended test to screen for colon cancer. So I don't think it requires anything additional in the families, but I think you should definitely do what the recommended guidelines are. So everyone who's at least got to 50 should rush off and have an endoscopy or a colonoscopy or something like that, or at least some of the blood or stool tests which are available for the disease now.
I tested positive for CDH1, and I have a cousin who had lobular breast cancer. When she went for some genetic testing, they also tested her for CDH1 and came back with inconclusive. Is there such a, you would think it would be a yes or no?
So you have
I have CDH1.
You have CDH1, and your cousin.
Does have.
It sounds unusual. The inconclusive is one of those missense mutations I mentioned before, where the mutation doesn't just destroy the protein, it's kind of makes it a bit funny shaped, not quite right, and other ones which require a lot more work to try and understand if they cause the disease. But I would have thought she would have the same mutation as you do.
Now, my geneticist said that she ought to go to a different laboratory because there can be differences between labs because of the protocol they use to do the testing.
Did they test her for your mutation, or did they test the whole gene? Do you know?
That I
Don't know. Yeah. So, if your mutation is a clear, truncating, nasty mutation, then
just tested also positive.
Right. Okay. So then I would expect they would test her for that mutation. If she has it, then she is at high risk. But they may have looked through they may have not seen that mutation. She may have been negative for that, but they may have looked through the whole gene and found another change which they didn't quite, a missense change which they didn't quite know was nasty or not. So it's an unusual one. So
Have a retest.
yeah, have a retest for your mutation. Make sure it's your mutation that they're testing for, and ask. I mean, you send me the information you like, and just try and find out what they meant by the other mutation
That's
being.
trying to get the test results from the labs and send to my geneticist.
Right. Okay. Good. Yeah. No, that's unusual.
When you find out you have the CDH1 mutation, there are all sorts of places that want you to register that you have it, that you keep a data bank of the information. How do research, and obviously you want to do that because researchers want that info. There just seem to be like so many of them, and different ones in different countries, and is the information amassed by anybody, and how is it handled, and do you share tissue samples too? How do you store?
Yeah, it's still completely disorganised, and it's something we're most concerned about, and I think it might start to tidy up a little bit now. We have the Portuguese group has volunteered to kind of lead the charge on maintaining the database of the families, and so we're hoping that all other smaller databases will hand their information through to the one place. That's all held in one place, and I mean these things take time, and often people don't like to do that. So it may not be straightforward, but we certainly are trying to get a single database for that. And as for tissue collection, it really is there's nothing at the moment which is systematic for tissue collection. It would really be more if we can identify individuals who had the mutation, would just go to them directly and ask them to contact their hospital and try and get the tissues for us, because when the surgery is done, they will keep samples behind in their archives. So at the moment there is no formal tissue banking at all, but there are some repositories in different places, but nothing centralised at the moment.
Are there any ideas about why some families present with strictly breast cancer versus strictly stomach and then mixed? Is there any ideas about why that?
No, there's not really. I mean, it might just be luck. Or it might be environmental factors as well. Like in our New Zealand Maori families, we didn't see the lobular breast cancer for quite some time. We saw, I think there was one person in that big pedigree who had lobular breast cancer, but we didn't think too much of it at the time because just one in a sea of stomach cancers. And what we think was going on there, because we're seeing more of them now that the people are surviving, living long lives, we're starting to see the lobular breast cancer turn up. So it's the second cancer for them. It comes in afterwards, slow to develop. But what we think, why we didn't see it earlier, is that Maori people tend to have big families. They tend to have families young. They tend to breastfeed for longer as well. So these are all classic protection factors for breast cancer. So women who have kids at an early age, breastfeed for a long time, have lots of kids, have less chance of getting breast cancer. So we think it was just really that these Maori women tended to have big families, and so they had a kind of natural protection from lobular breast cancer, and so we didn't see it so much. So that's one reason.
Harry, in follow-up to the question about the registry, the database, is there a way that No Stomach for Cancer can help facilitate getting patients' data into the database in Portugal?
Yeah,
Providing the appropriate procedure or method to do that?
Yeah, I think so. I mean, because what worries me about the kind offer from the Portuguese group is it's going to be a lot of work for them, and they're research side of that. They're at the bench doing experiments, and they're trying to run this database as well, and it's not easy to do that. So what would be quite good is if there was a mirror of the database kind of held by No Stomach for Cancer, or at least the form which people could fill in online on your website, and then that could just be shipped. The data could be curated, and that could be shipped across to the Portuguese after that. So I think it would be very useful if you were a face for a lot of that data collection. Yep.
Question. You mentioned a lot about how missense versus nonsense. What's, I guess, the real, clarification on exactly what does that really mean for CDH1 folks? Like, I believe my wife, we just recently received paperwork on it, and looking at exactly where, what gene it is. I'm trying to, ascertain what is missense versus nonsense.
Right.
That really applies to her.
Right.
For HDGC.
Okay, so the report should be quite clear whether it's a missense or nonsense mutation. It should state what it is.
Well, it says it's exon 6, but
Yeah.
Pathogenic.
Okay, so that would mean it's probably a serious truncating mutation. So what we mean by that is a missense mutation is one where the sequence has changed, but the protein is still there and it's just not working quite right. And other ones which are hard to interpret. If it's called pathogenic, it means it's going to be a truncating mutation, which means it stops and the protein is just lost, it's not there. So they use the word pathogenic to say it's capable of causing disease. And so that would be, we can double check what the mutation is, but that would be a serious truncating mutation, which would increase your risk.
And the exons, are they involved in the different
Yeah, so
risks?
the exon just refers to the location. I wonder if I might just skip back. It just refers to whereabouts in the gene the mutation occurred. Here. Yep, so you can see there, I've written exons 1 through to 16 here. So exon 1, this refers to the first part of the gene, or the first part of the protein. Exon 16 is the last part of the gene, and they're called exons. It's just to do with the way the gene is made and structured. But so it's divided into these 16 little discrete chunks of DNA sequence, and so it was what, exon 6, you say? Yeah. So your mutation is in this part of the gene, which means if your mutation is truncating or pathogenic, it probably means that that when the protein is made, it'll get made up to here, then nothing more after that. You'll get a little small bit of protein made, but you won't get, all this part won't be part of it. So you'll have a protein which, rather than being this long, will be this long, which means all the functions that the protein needs are missing. So it just doesn't work anymore.
Just about future, I don't know if you know anything about, so you mentioned IVF. Do you know anything about the risk of lobular breast cancer with going IVF?
The risk of
Developing lobular, if it increases your risk at all?
Oh,
I'm not sure if you
I don't know. Sorry.
Yeah, it's okay.
Yeah, I haven't heard. Sorry.
Do you know the latest statistic? I know each of us, when our families were diagnosed, we heard there were X number of families who have this mutation in the world. Is there the latest number you know?
No, it's really disturbs me, but we don't have that number. Initially it was quite easy because every new family got published, and so we could get the information, but now a new family has been tested and information is not made publicly available. They're tested by some big labs. They so far have refused to give me the information, so I can't do a count. So we are just guessing. So I'm thinking 350, 400 is my guess, but it's probably increasing by 10, 20 a month. Oh, maybe not. Maybe 10 a month. I think worldwide. I know, for example, in Paris, where they keep quite good records in Paris, France. They've got 55 families in Paris. We know that much. In New Zealand, we've got 18 families. So you could kind of do some sums based on the population to give you an estimate of how many there really are or really are going to be. At the moment, I think probably around about 400 known families. You all look exhausted. Fair enough. No, one more.
In your work with this New Zealand family, have you seen any improvement in the handling of late-stage cancers?
Of late-stage cancer?
Yeah. But I know over here they're not in favor of the guidelines suggesting surgery, but then again, I've read something that suggested that surgery in families, in familiar cancers, is better than with sporadic cancer, but that's just one team.
Since we've done the gene testing in that family, we've only had 2 advanced cancers in 15 years, so there's been no change in practice. What is I think important is in the old days, they didn't do complete gastrectomy, so if someone was found with a stomach cancer, they'd just chop out the tumour and leave the rest of the stomach there. And of course, you get a recurrence later on. There's a very high chance of a recurrence later on in the remains of the stomach. So now they, at least if someone's found with advanced disease, they'll do a complete gastrectomy and remove the risk of any new cancers coming along. But there's been no developments in chemotherapy, particularly in that. But again, the work we're doing on those drugs we're developing at the moment, we think they're going to be very useful for advanced disease as well. So we're hoping that as the work carries on, we'll have better treatments for advanced disease as well as the chemoprevention option.
What about the whole HER2 and MET amplification stuff too? And do you have any insight into any of that? Which I don't think I understand properly, but...
In relation to HDGC?
Just treatment in general.
Oh, okay.
And the gene mutation.
Yeah, I mean the whole world of cancer treatment is moving towards targeted therapies, and we identify the mutations in the disease, and so there are many mutations involved in cancer, and each cancer is different, and every patient is different. And so increasingly the trend is to get someone's tumour and search for the mutations which have occurred, and then choose drugs which match the mutation. So for example, if you have HER2 amplification, you get a drug which stops that event. So the whole world is moving towards that kind of personalised medicine where you look at the advanced tumour, you find the mutations which are present, and then you give drugs which match those mutations. So that's come along. It's not nearly as advanced in gastric cancer yet as in other cancers like breast and colorectal and lung, but it will come. So I think that speaking generally about cancer, I think I hate to put a number on these things, but I think in 10, 20 years' time, no, it's probably not 10, probably 20 years' time, I think we'll see in many cases, many cancers will be seen as being a chronic disease rather than a lethal disease. You'll treat it with a cyclone drug and another cyclone drug and another cyclone drug, and you'll always have cancer, but it will be managed and it will never get bad enough to kill you. So that's where it's going to head to. I think it'll be more like, it'll be seen more like diabetes in 20 years' time than a lethal disease the way it is now. You're worn out? All right, no further questions?
Don't go anywhere. Keep going. You can sit down, but we're still going to pick your brain. Okay. Can you guys hear me? Okay. Thank you very much. What more can we say? You've saved many people's lives in this room, and more people in our families who've yet to be tested. So thank you is really all you can say. A couple of the thank yous for today is
again, thank you to Eli Lilly for helping provide this opportunity for us to make this a free event for you. We know you incurred some costs getting here, and we appreciate that. But it really, with the support of them and the survey that they're giving, they want to support us, and so we're very, very grateful for that. Thank you again to everyone who participated and spoke today. There's nothing more valuable than connecting with people, helping us carry out our mission of doing that. And, I've listed where people came from. This isn't everyone who happened to live near Philadelphia. People made long journeys to get here for a number of reasons, and we're so grateful. And really just to everyone. As far as after you leave here today, we hope that you will continue to stay part of the No Stomach Cancer community and become more involved. I want to just remind you of, and if you don't know about it, November 11th, it's the first Saturday of November every year. We have our annual walk wherever you are in the world. You can get one going. We're going to be working on that in the near future as far as, helping and starting to promote it and letting you know how you can be a part of that, as well as volunteer opportunities. We really want you to continue to share your story. Today was about sharing our stories, and Parry talked about the Maori family's stories, and that's really the best way to get information out to people and educate them. Please watch for future spotlight events. We have planned last summers, and this one's around our annual board meeting. We get together as a board one time a year physically. The rest of our meetings are done through technology. So we want to be, fiscally responsible and work in our plans, but we also want to connect with you. So each year our goal is to spread it throughout the country. So if you can't make this one, or someone's in another part of the country, hopefully eventually we'll get to where they are and can connect with them. And then really just please talk to each other. Take this opportunity to connect with other people. Please introduce yourself. If you haven't met board members, we want to talk to you. We want to know your needs. Let us know how we can help you better. And I just wanted to indicate the topics that we're going to have at different tables. So someone might come over and plop down a table tent with a topic. You can stay or leave, but here are the different topics, and I'm just going to ask each person who's kind of the table leader to stand up so people can put a face with a name. So I think Parry Guilford. He's going to be speaking about any HDGC questions you may have. Gretchen Borsey, who you heard from earlier, as far as her focus will be breast cancer, so if you have any questions about the lobular breast cancer. Donna Walsh over there, she's on our Scientific Advisory Council. She's a nutritionist. She will be speaking on any concerns on that. Melanie Torborg, who you heard from, a board member, is going to be talking about the perspective of a parent dealing with children with the CDH1 mutation. Hannah Torborg, who you also heard from, is going to be, she carries a CDH1 mutation, as she mentioned, and if there's younger people around who have concerns, want to talk about that. Dr. Natasha Santos, who's on our board of directors. Natasha, there you go. She's going to be looking at the emotional or psychosocial aspects of dealing with HDGC. And then Roger Byers, who's in the back there, he's also on our board, and he's just going to answer any questions you may have as far as about No Stomach for Cancer, what we're doing, ways to get involved. And John Florine, who's also, can you stand up, John? Thank you. Our executive director, if you have any questions or you want to talk to him about anything, we'd love to talk to you. So at this point, there's food in the back. Thank you. Whenever you stay till 7:30, however long you want to stay here, and just thank you so much. We really appreciate it. Thank you.